Hello, in this video we'll prove that any regular language is a context-free language. For this, we will show how to find a context-free grammar if we have a regular language. As you may know, a regular language is a language that can be described by a finite state machine. If there's a finite state machine, let's find it and then let's show how to convert this finite state machine to a context-free grammar. Let's take, for example, the set of binary strings with odd number of zeros. For this language, we may write the following finite state machine. We may have two states A and B, and we may go from the initial state A to B if we will find a 0 in the input, and this state B is accepting since we have 1 0 here. There may be some ones before this 0. Also, we will accept if there's a sequence of ones after this 0, and this B is accepting. If we will have in the input another 0, we will go back to the state A, from which we will go to the state B with another 0. So the final number of 0 will be 3. If we will have a fourth 0, we will go back to A, and we will go back to the accepting state with the fifth 0. We will accept only odd number of zeros. For the ones there may be in any place with any occurrence. There's a simple way here to write a context-free grammar. We may use the same name of states here, A, B, as the names of variables in the context-free grammar. The start state here is A, so the start variable in the context-free grammar will be A. We will write A is substituted by 1A, since we have here an arc going from A to A with the symbol 1. If we see in the input 1, we will go again to the symbol A. If we see 0, we will go to the state B. So here again, if we see 0 from A, this A will be substituted by 0B. Now for the symbol B here, it will be substituted by 0A, since we have in the finite state machine this transition here, 0 going to the state A. If we see 1, we'll stay in the state B, so we'll write or 1B. Since B here is the final state, it is an accepting state, we will write B has the rule epsilon. So this is a very simple way to obtain a context-free grammar if we have a finite state machine for the language. Let's now take another example. The binary strings that contain at least 3 ones. In each string, we will have 3 ones, 4 ones, 5 ones, and etc. So we may write the finite state machine this way. We may have the initial state A, which will lead to the state B if we will see 1, but we will stay in the same state A if we will see 0. From B, we will go to C if we see 1, but we will stay in the same state B if there's a 0. From C, we will go to an accepting state D, since we have already 3 ones, and we will stay in the same state C if there are some zeros. From the end here, we may also have another list of zeros and ones. Doesn't matter what is the number, since we have reached the state D with 3 ones. Now we will apply the rules for the conversion from this finite state machine to a context-free grammar. We will take the same variables here, A, B, C, D, from the names of the states A, B, C, D. And we will say that A will be substituted to 0A if we see a 0, because we have this arc here that mention that from A, if we have a 0, we will stay in A. And the second rule for A will be 1B, since if we will have a 1 in the input, we will reach the state B. Now for B, it will be 0B or 1C here. And for C, it will be 0C or 1D. We'll write the rules here. And for the final state, D, it will be D is substituted by 0D. If we will see a 0, we stay in the same state D, or 1D, since we will also stay in the same state D if we see a 1 in the input, or epsilon, since it's the final states. So since we have this way to convert from finite state machine to a context-free grammar, we have shown that there is a way to write a context-free grammar for any regular language. So we can say that all regular languages are context-free.